So today we're going to talk about the output waveform of the inverter, and we're going to examine the inverter's output waveform together. As you can clearly see in the provided image, here it's distinctly showing us the precise output waveform of the inverter, and we genuinely want to understand how this particular waveform is meticulously generated and carefully examine together how it is precisely created. Alright, as you can see in the image. Here, it's showing us the input of a three-phase inverter, which is made up of several diodes and capacitors. When we connect three-phase power to the input of the inverter, these diodes and capacitors rectify the power, and ultimately, a DC voltage is produced for us. Here, a number of switches are used, and in practice, we use IGBTs for this purpose. A very important point I need to mention about these switches is that they operate in pairs in a complementary, not manner. That is, S1 and S4 are complementary to each other. S3 and S6 also operate in a complementary way. S5 and S2 are also complementary to each other. So, when we say they are complementary or operate in a not manner, it means that when switch S1 is closed, S4 must be open, or when S1 is open, S4 must be closed. If it ever happens that both S1 and S4 are closed at the same time, our inverter will be damaged. So, since that's the case, in practice there are 8 possible states that can occur, and you can see these 8 states in this table. One of these states is when S4, S6, and S2, that is, these 3 switches, are closed. S1, S3, and S5, what should they be for us? They should be open. This is the first state that you can see here. Well, if these 3 are closed, the voltage that appears here is actually just our ground, so no potential difference is created here. In practice, we can say that VN, VBN, and VCN become what value? They become 0 because there is no potential difference and these 3 are connected to ground. And if we consider another scenario, that is, S1, S3, and S5 are closed. S2, S6, and S4 are open. So, consider this situation. Well, what happens in this case? Again, RVA, VB, and VC each become a logic level. Again, in this case, we don't have any potential difference, and because no potential difference is created here, our VN, VBN, and VCN values also become 0. Alright, we've examined these 2 scenarios together. The other cases remain, which we'll go over together in the next slides. This is showing us a situation where VAN, VBN, and VCN are all 0. Alright, let's examine the first scenario together. When switches S1, S5, and S6 are closed, we want to see what happens. This first diagram shows us the status of the switches. If S1 is closed, its value becomes 1. If S5 is closed, its value becomes 1. If S6 is also closed, its value becomes 1. The rest of our switches, which are open, have a value of 0. The next diagram shows us the values of VAN, VBN, and VCN. Vn is the potential difference that occurs between these 2 points. So, we say if switches S1 and S6 are closed, a potential difference is created between these 2 points, which is equal to 1/3 of our DC voltage. Also, if switches S5 and S6 are closed, a potential difference is created between these 2 points as well, and again its value is 1/3 of VDC. And finally, between VB and the neutral point, a potential difference is also created. Since the direction of our current has reversed, and the current is now flowing out from this part, this voltage becomes negative and its value is minus 2/3 of VDC. Now, let's analyze these on the graph together. We said that our VAN is 1/3 of the DC voltage. Our VCN is also 1/3 of the DC voltage, and our VBN is minus 2/3 of VDC, as you can see. And these are the graphs that you can see here. VB, VBC, and VCA. VB, it's the difference between VAN and VBN. If we subtract these two from each other, let's see what happens. It becomes VAN minus VBN, but since VBN is negative itself, so it's like we're actually adding these two together. This value is 1/3, this value is 2/3. So if we add these two together, in the end we get the DC voltage value. That is, it gives us VDC, and this graph, which shows the VBC voltage, illustrates that for us. VBC means the difference between VBN and VCN. If we want to subtract these two from each other, this is what we get. VBN minus VCN ultimately gives us minus VDC, as you can see here, and this graph is also VCA, which is VCN minus VN. If we subtract these two, the result is 0. All right. The second scenario is when switches S1, S6, and S2 are closed, and the other switches are open. Now, let me point out here that we keep the previous scenarios, and these new scenarios are added to the previous ones. When S1 is closed, its value here becomes 1, and when S2 is closed, its value also becomes 1. And when S6 is closed, its value also becomes 1. The other switches that are open have a value of 0, as you can see here. Alright, so when switch S1 is closed for us, since these two switches are also closed, a potential difference is created between these 2 points. So, if we want to find the value of Vn, Vn will be 2/3 of VDC. That is, just as you can see here, its value becomes 2/3 of VDC, and in this part, since the direction of our current has reversed, if we want to find the potential difference between these 2 points, VBN becomes negative, and it will be minus 1/3 of VDC. At these 2 points as well, since the direction of our current has reversed, VCN also becomes negative and turns into minus 1/3 of VDC. This is exactly what you can see here in the diagrams, and as for VAB, VBC, and VCA, as we explained earlier, VAB is the difference between these two graphs. VBC is the difference between these two graphs, and finally VCA. It's the difference between VCN and VN, as you can see here. In the next slide, S1, S3, and S2 switches are closed for us. The other switches are open, so S1, S2, and S3 each have a value of 1. Since our other switches are open, their value is 1. And when switch S1 is closed for us and S2 is also closed, here a potential difference is created, and the value of this potential difference is 1/3 of our DC voltage. In this case as well, similarly, when switches S3 and S2 are closed, a potential difference is created across these 2 points, and our VBN value becomes 1/3 of our DC voltage. And here, since the direction of the current has reversed, the voltage we have, VCN, is negative and equals minus 2/3 of VDC. That's exactly what you can see here on the graphs, and this VAB, as we mentioned, is the difference between VN and VBN, which in this case is 0. BC is the difference between VBN and VCN, and VCA is the difference between VCN and VAN, as you can see here. In the next scenario, switches S3, S4, and S2 are closed for us. That means their value is 1. The other switches have a value of 0, and when this switch is closed, since these 2 switches are also closed for us, here, in fact, a potential difference is created whose value is 2/3 of our DC voltage. As you can see, in these 2 sections as well, that is VAN and VB and VCN, since the direction of their current has reversed, a potential difference is created in each of them. In VAN, its voltage becomes negative 1/3 of VDC. VCN also becomes negative 1/3 of VDC. That is exactly what you are seeing here. And as we said, these also show us the difference between these graphs. The next case. S3, S5, and S4 are the ones, and if they are closed, their value becomes 1. The other switches that are open have a value of 0. And if this switch and this switch are closed, a potential difference will be created between these 2 points. Its value will be 1/3 of VDC. Also, when S5 and S4 are closed, a potential difference is created between point VC and N as well. The value of this potential difference is also 1/3 of VDC, and finally, the voltage between VA and point N, which is VAN, becomes negative 2/3 of VDC, as you can see here. In the next state, S5, S4, and S6 are closed. The other switches are open. Again, we can say that since S5 is closed here, and S4 and S6 are also closed, a potential difference is actually created between these 2 points. Its value becomes 2/3 of VDC. And in each of these, again, a separate potential difference is created. Our VAN becomes minus 1/3 VDC, and our VBN also becomes minus 1/3 VDC, which, as we mentioned, shows us the difference between these graphs. Alright, so we've reviewed those 6 remaining states together here. This particular slide actually shows the general case and clearly displays all 6 distinct states for us, as you can readily observe here. Now, in order for our waveform to be complete, these states keep repeating. That is, the next state is a repetition of the first state, where S1, S5, and S6 are closed for us, and the other switches are open. And as you can see, our VN is 1/3 of VDC, our VCN is 1/3 of VDC, and our VBN is minus 2/3 of VDC, and this also shows us the difference between these 2 voltages. Here as well, it shows the difference between these 2 voltages in the same way. And finally, this one shows the difference between VCN and VAN. Well, these steps keep repeating. That is, again in the next state, S1, S6, and S2 are closed. The other switch is open, and our diagrams keep getting completed. And finally, we arrive at this waveform that you are seeing. Thank you for watching. See you next time.